the cross product of two vectors is performed, the resultant vector can be written as shown here. Here, modulus P modulus Q sine theta is the magnitude, and n is the unit vector. So the resultant is also a vector. We know that the cross product of vectors P and Q is a vector perpendicular to both of these two vectors. We also know that the unit vector n in the cross product of two vectors P and Q is also perpendicular to the vectors P and Q. Hence, the cross product of two vectors P and Q and the unit vector n are collinear. Consider two non-zero vectors P and Q. If the two vectors are parallel to each other, then the angle theta between them is 0. Since sine 0 is 0, the cross product of two parallel vectors is a zero vector. Thus we can say that the cross product of two non-zero vectors is a zero vector if and only if the two vectors are parallel to each other. This leads to some interesting observations. Since every vector is parallel to itself, the cross product of a vector with itself is a zero vector. Also, the negative of a vector makes an angle of 180 degrees with the given vector. Since sine 180 is also 0, the cross product of a vector with its negative vector is also a zero vector. You already know that unit vectors along the x, y, and z axis of a three-dimensional coordinate system are denoted by unit vectors I, j, and k, respectively. From the discussion so far, it follows that the cross products of unit vectors I, j, or k with themselves is a zero vector. Now consider two vectors P and Q that are perpendicular to each other. This means that angle theta between them is 90 degrees. Since sine 90 is 1 and n is a unit vector, the magnitude of the cross product of two mutually perpendicular vectors is equal to the product of their magnitudes. If you know the magnitude of the cross product of two vectors and the product of their modulus, you can find the value of angle theta between them using the formula shown here. You already know that the cross product of vectors P and Q, when P rotates towards Q by angle theta, is given by the formula shown in equation 1. The vector representing the cross product of vectors P and Q is in the direction of unit vector n. Observe what happens when vector Q rotates towards vector P by angle theta. In this case, the vector representing the cross product of vectors Q and P points in the direction of unit vector n dash. Comparing the two figures, we can see that vectors n and n dash are in opposite directions. Putting vector n dash equal to minus vector n in equation 2, we get equation 3. Comparing equations 1 and 3, we find that the cross product of vectors P and Q is equal to the negative of the cross product of vectors Q and P. This leads us to the conclusion that the cross product of vectors is not commutative. From the discussion so far, we can again make some interesting observations about unit vectors I, j and k pointing along the x, y and z axis of a three-dimensional coordinate system. From the property of cross product of perpendicular vectors, we get that the cross product of unit vectors I and j is equal to unit vector n that is perpendicular to both vectors I and j. Since unit vector k is also perpendicular to vectors I and j, we can say that the cross product of unit vectors I and j is equal to unit vector k. From the property that states that cross product is not commutative, we get the cross product of vector j and vector I is equal to the negative of vector k. Similarly, we arrive at the results shown here. Now, let us explore another interesting property that states that if two vectors p and q form the adjacent sides of a triangle, then the area of that triangle is equal to half of the modulus of the cross product of vectors p and q. To prove this property, we draw QR perpendicular to two vectors given in component form. Consider two vectors A and B as shown. Let us consider their cross product. We know that cross product is distributive over addition. Using the distributive property, we can expand the cross product as shown. We know that unit vectors I, j and k are mutually perpendicular to each other. We also know that the cross product of a unit vector with itself is equal to 0. We have already observed the cross products of mutually perpendicular unit vectors as shown here. Substituting the corresponding values, we get the equation as shown here. On simplifying, we get the cross product of vectors A and B as shown. The cross product of two vectors A and B can also be expressed as a determinant as shown here.